We're considering pipe flow from an engineering perspective. We don't want to solve Navier-Stokes equation, but we want to have a handy way to really do the design for the length of the pipe and choose the proper pump to basically achieve the volume flow rate that we need. And in general, the pipe can go uphill or downhill. And say like this is the pipe that's going uphill, and then we may have valves or T's, right? Or bends along the way of the pipe, or it could be a cross-section change from a larger pipe to a smaller pipe, from smaller pipe to a larger pipe, all kind of different things that basically affects the flow field inside the pipe. So if the pipe is uniform, has a uniform cross-section without any appendages or anything, then we have losses due to friction, right? But as soon as we introduce a little valve or any non-uniformity in the cross-section of the pipe, then there are additional losses because of this non-uniformity and the effect that this non-uniformity has on the flow field. These losses will be introduced. Let's start from the energy equation. So as we discussed, energy equation. It's looks like Bernoulli's equation, P1 over gamma, and we said gamma is rho g plus V1 bar squared divided by 2g. We put alpha 1 here, plus Z1 is equal to P2 over gamma plus alpha 2 V bar 2 to the power 2 over 2g plus Z2. This equation is valid if there is no energy losses in the system. And because of the losses, we're going to add the so-called head loss here. That has the total energy loss. The one term that has everything, right? And this term can have contribution from different sources, right? Now, just a little reminder here that we introduced alpha 1. Alpha 1 is because appears or is non-unity if the velocity profile is non-uniform. If velocity profile is uniform, alpha is equal to 1. If velocity profile for any reason, if it's a pozoid flow, if it's a turbulent flow, for any reason, if velocity profile is not constant across the pipe, then alpha is going to be greater than 0. And we know that if we introduce viscosity, the velocity at the pipe surface is 0. So definitely there's going to be velocity gradient. So in real pipes, alpha is always greater than 0. But again, the more non-uniform the velocity profile, the higher the value of alpha. So for example, for the case of, let me ask you this question. Pozoid flow versus turbulent flow. Which one has a larger alpha? So this is a velocity profile in a pozoid flow. It's parabolic. And then in a turbulent flow, we said that the velocity here is kind of like a more uniform, right? So let's assume that we have a same volume flow rate. So the average velocity is the same in both cases. Of course, the alpha for the case of turbulent, and this is alpha for the case of pozoid flow. Because pozoid flow is more non-uniform, alpha, the turbulent flow is more or less uniform. So alpha of turbulent flow is more or less close to 1, whereas we calculated the alpha of pozoid flow to be 4 over 3. So alpha of pozoid flow, a more non-uniform flow, is higher than alpha of a kind of a uniform flow. Okay. Anyways, so let's move on. Now, speaking of the head loss, head losses can be due to like a friction along a uniform pipe, as I mentioned, and because of non-uniformity in the cross section or stuff that we have on the side of the wall. So therefore, it's customary that we divide the H loss or head loss into two categories: the major losses, which is due to friction along the pipe, and minor losses due to valves and T's and bends and change in the cross section and so on and so forth. Let's talk about the major losses. So if there's a loss inside the pipe, what happens is it appears as a pressure drop. If there's no head loss, what happens is that we don't need any force to move the flow inside the pipe. There's no resistance. Resistance comes from the friction, right, with the wall. right? And therefore, if there is friction, then that's why we need to basically push the flow in order to achieve a certain volume flow rate, right? So basically, the head loss is proportional to the pressure drop, right, due to viscosity inside the pipe. So one interpretation of this term is, well, how much pressure drop or how much pressure difference do we need to achieve a certain volume flow rate? And then to make the dimensions to work, we divide this by rho g. So this is a delta P due to viscosity, the delta P that we need just because there's a viscosity inside the fluid, right? Or the fluid has the viscosity. This pressure, delta P, is going to be 0 if viscosity is 0. Remember, this is different than the pressure due to the height change, right? So this pressure needed to pump fluid to a certain height exists no matter if you have viscosity or we don't have viscosity. That's a different story. That's a potential flow, right? But this delta P inside HL is the pressure drop due to viscosity. This pressure drop goes to 0 if there's no viscosity. All right, so now we know from the analysis, the dimensional analysis in the Moody chart, that the friction factor as a function of Reynolds number gives us a measure of the pressure drop due to viscosity. Now let's do this. Let me just there are 3 different cases that can exist. Sometimes delta P is given to you, so I know that what exactly delta P is. If delta P is given, then HL is simply delta P over rho g. So if delta P due to viscosity or viscous effect is given, then all you need to do is just divide that by rho g, and that gives you the answer. Sometimes we can put a shear sensor on the wall of the pipe and measure the shear sensor. And let's see if we can estimate the HL based on the shear sensor. In order to do that, I would like to note that the average shear sensor on the wall has a simple relationship with the pressure drop. So if we need a pressure difference between the 2 sides of the pipe, delta P, because of viscosity, this pressure drop, right, it results in a force in the x direction. How much is the force? If this cross-sectional area is A, the force is delta P times A. Now, this is a fluid flow with a uniform speed. There's no acceleration. So therefore, this force needs to balance with a counteracting force, right? The counteracting force balances this pressure so that the net force is 0, and as a result, there is no acceleration. Where does this counteracting force come from? Well, that comes from the friction of the wall, right? So the wall is kind of pushing the fluid in the opposite direction, or opposing the motion of the fluid, right? So that's how the force balance come from. Now, the shear stress, we assume there's an average shear stress called tau W, and then the total area is 2 pi r times the length of the pipe. Okay, so therefore, delta P, and then A is pi r squared. That has to be equal to tau W times 2 pi r times L. I cancel pi with pi and one of the r's with this r. And therefore, what I get here is, therefore, delta P is equal to tau W 2L over R. 2 tau W L over R, and that's going to give me the delta P. Now, this is a good result, so it deserves a little box. All right, so if tau W is given from a wall shear sensor, then all I need to do is to multiply the tau W times 2 times L and divide it by R. That gives me delta P, and therefore from here I can calculate H loss. From here, head loss is delta P over rho G, and that's going to be 2 tau W L over R rho G. So if tau W is given, I put the result here. H loss is going to be 2 tau W L divided by R rho G. All right. Now, sometimes the only thing we know is the average velocity, right, or volume flow rate. If volume flow rate is known, average velocity can be calculated by dividing the volume flow rate by the cross-sectional area. Now, in this case, what we do, we calculate the Reynolds number. So Reynolds number is equal to rho v bar d over mu. Then we go to the Moody chart. From here, we can calculate the friction factor, F. Now, what is F? F is delta P over 1/2 rho V squared times D over L. All right. Now, if F is calculated, once we have F, we can then calculate delta P. So delta P is equal to F times 1/2 rho V squared times L over D. All right, and then for the friction factor, what we're looking for is HL is delta P. This is delta over rho G. So that's F 1/2 rho V squared over rho G times L over D. So that becomes F V2 over 2G. And this is V bar, of course. These are all V bars times L over D. All right, so if V bar is given, then this is a procedure. So we follow from here, and then HL, or the head loss is given by F V bar to the power 2 over 2G times L over D. And of course, if F is given, that's the way we're going to proceed. So this is a major loss part of the flow inside the pipe. For the minor loss, what happens is that usually an experimental empirical coefficient is given, and that coefficient is usually we show it by KL, and KL is the head loss due to the presence of that bend or T or whatever that we have divided by V2 over 2G. V2 over 2G. So KL, is given in a table or provided to you anyway. So all you need to do is to multiply by KL. So HL, this is for minor. So therefore HL is KL times V2 over 2G. And therefore you're going to basically add that into the equation. So the HL total, therefore, is going to be the HL major plus HL minor. And you basically substitute in the equation, and you're going to be basically all set to move forward.